from here, it is a magnifying, you could be able to understand better way. Here you see this much of volume getting up from the water. And the same amount of the volume will come inside the water now. So there is no net change of volume. So V is constant. What is the V? V is the volume of the displaced liquid by the solid. That is constant. But you see here, the center of buoyancy previously was at here. Now it is shifted to here. Now it is shifted to here. But G position is not changed. Center of gravity is not changed here. So this is the axis, central line. This is a central line about central line, better to write it central line, about which the symmetry is established. And from the new CB, new center of buoyancy shifted, displaced here. From the new CB dash, if you draw one perpendicular line, it is intersecting the center line. And the point is known as the metacenter M. The point is the most important point, metacenter. And the distance between the G and M is a deciding factor of the stability in here. Which kind of stability? GM is the deciding factor. So that is only the deciding factor in here. So this is the consideration we are taking here. Now we'll see previous condition, what was the position of the center of buoyancy, and now in this condition, what is the position of the center of buoyancy. So how much it got displaced. One analysis we are going to take it now. So the analysis we are going to take it now in this manner. Metacenter. So metacenter, hopefully you have got it. Metacenter is denoted by M, and metacentric height is denoted by GM. The distance between the metacenter and center of gravity along the central line is known as the metacentric height. What I'm telling? The distance between metacenter and center of gravity along the central line is known as the metacentric height. So here, what is the metacentric height? This mg or gm, this distance is the metacentric height. This gm, the metacentric height, it is greater than 0. Because m is above g. If m is below g, it is less than 0. This way, the concept is complete. So better to see here. So previously the condition is the initial condition. Is the initial condition. So initial condition, that much amount was submerged condition. This is the submerged position. So here we take one small elemental portion. You take it at Z. At x is equal to, at x distance, dx. You took it. One small elemental area, you are taking it. So where is the position of the center of buoyancy? Where is the position? So for getting the position, if you have to go for one more thing, that's some I have to draw now. The plan view of this. So plan view of this is like this. It is like this. This boat plan view is like this. This is the Z direction. This direction is the x direction. And it's a plan view. So plan view means okay. Redraw this thing. So from here, direct. What is this axis? This is not Z axis. It's a different axis. The plan view. So sorry, it is separate. Z axis up to this. Here it is a plan view. So plan view means this is the y axis. You cannot see this axis. Perpendicular here in this figure, it is a perpendicular to the plane. So that's it. So this is the y axis. So here you take one's small elemental area. Like this. Area. Plan view, we are looking, it looks like this. In the plan view, it looks in this way. That is nothing but dA. So where is the location of the, now here, where is the location? The location of center of buoyancy. We have to search for the location of the center of buoyancy. So in this condition, the location of the center of buoyancy is equal to 1 by V. If you remember this thing, we have to do it like this way. X into dV. What is dV? Z into D. So X, Z, dV. So dV is the dA into Z. dV is equal to Z into D. That is the equation 1. So in this condition, the position of the buoyancy, in this condition, the position of the buoyancy is at here. This is the position of the buoyancy. 1 by volume, xz. Now you give one tilt here in this way. After giving one tilt, you see this portion is coming out of the water and this portion is coming in. So your consideration is you previously taken this portion, this element. Here you see this element you have taken. Now it is inside the water. So from here to here already, Z you have considered, and that is the remaining portion also. This portion is also, extra portion is coming here. This is the extra portion. Z is already defined previously. And this extra portion also coming inside the water. That's why this B, center of buoyancy, changes. Change its position. And what is that? This is the X. This theta, you take it the theta. This theta. So this portion is nothing but the X tan. Because you tan theta this by X, so this portion is nothing but X tan theta. So now the new height is Z plus X tan theta into dz, new volume. So X B dash is equal to 1 by, because the total volume is not changing. The total volume is not changing here. Because you see this portion, the same volume is coming out, same volume is coming in. But here, the amount of the strip height is changing. Now the new strip height becomes x tan theta plus z. That is the new volume. And this volume is at same x-axis. X into distance. Distance is the same x, but strip height is changing. So that is the new position. That is the equation number 2. So this is for the initial position of center of buoyancy. This is the new position of the center of buoyancy. So initial position of center of buoyancy, new position of the center of buoyancy. So what is the changed? So what is the displacement of the center of buoyancy? That is the displacement of center of buoyancy. xb dash minus xb. That it is nothing but is equal to 1 by volume x square tan theta dA. And it out because xz dA will be cancelled out. So that is the displaced. So if you write it here, xb dash or new position of center of buoyancy and old position of the center of buoyancy is equal to 1 by volume tan theta x squared d. Tan theta is not dependent on this area because theta is maybe arbitrary, no change, any kind of tilting you can give. So tan theta is out of integration. Okay. X squared d. What is x squared d? X squared dA. So this distance is the x. So x squared dA of integration is nothing but Iyy. Iyy dash. Second moment of inertia or second area moment. Second moment of area, better to write it there. Loosely we are telling that moment of inertia, but it is a second moment of area about the YY axis. So you have to go for the plan view. You have to go for the plan view in this case. YY axis is required. And theta, in the theta, if it is a small theta, so tan theta you could be able to write it theta. So it's a small theta. So this theta into V into Iyy. Iyy. Now you look for it. So previously where XP? Previously XP was at here. Center of buoyancy was at here. We are not XP, we are not considering center of buoyancy is here. G was at here. Okay. So previous condition, here was the B, here was the G. After rotation. Now B comes in some position, B dash. And from B dash, if you draw one perpendicular line, where it is meeting, there is metacenter. We have already defined it. And this is the xb dash minus xb, this distance. So BB dash. So BB dash is nothing but xb dash minus xb. And what is this angle? That is the tilting angle, theta. This angle is nothing but the tilting angle, theta. Same angle, this angle, all are the same. Theta, tilting angle. So BB dash, if the theta small already we have informed, We have informed theta small. So BM into theta will give this. It's like arc. It's like an arc. So BM into theta. So BM into theta. So into theta will gives you BB dash. Just like arc. It's a radius and angle. So radius into angle will gives you the arc. So here theta will be cancelled out. So distance between the BM is equal to IYY by BM we could be able to write it GM plus PG equal to IYY. The most important equation, I'm writing it now. Metacentric height GM is under the box. The metacentric height GM is equal to IYY, second moment of area with respect to the axis. Which axis? Second moment of area. Which area? First of all, the area on the floating area. Second moment of floating area with respect to the axis, which is about which is there is a rotation. About which axis it is rotation is there? Is this kind of tilting we are giving about which axis? Perpendicular to the plane axis. That is nothing but the y-axis. So about rotational axis. So IYY can be defined as the second moment of area, floating area about rotational axis, divided by the volume of the liquid displaced by the solid, minus B, distance between the center of buoyancy and center of gravity. The most important equation we are getting in this way. We are getting in this way. That is the case here. One more experimental way we could be able to get the GM. I hope you've got this thing. Just here, then I can rub this thing. One more experimental way we could have able to finding out the GM. How it is? Some more question is also coming regarding this. Let you take some loose weight is there. Over the ship, there is some loose weight. Loose weight P. Okay, P is there. So previously G and B was the same position. So here it is G, here is B, same position, no problem with it. Now what happened? P suddenly come here. X, it moves by X distance. This weight is suddenly moves by X distance. And the weight of the ship is given as the W. Weight of ship is given as the W. In such a situation, what is happening? It is trying to find another equilibrium condition. So your G, in that case, your G will be shifted and B also will be shifted. In this case, your G and B both will be shifted. Why? Because your weight, previous the case, weight no changes. But now the disbalance, some loose weight is coming. other side. So center of gravity will be changes. So this is the loose weight actually. So previously the G was at here. Now the new G is at in this equation. And B was at here. Now the new B is. Now this G and B. Now this GB will be here slightly displaced. Okay, no problem. And this is the metacenter. This is the metacenter. So because of this, some angle created, that is the theta. This angle theta is known as the heel angle. Heel angle. So as the P weight is displaced by X, because of this, it is happening. So this P weight is displaced by X, so P into X, it creates a moment. This moment will be W into GG dash. Because W is changed from G to G dash. The displacement of the, because of the weight, the moment, this will be balanced by each other. Total weight of the seam. Here W is the total weight of the seam. And P is the loose weight, which is displaced across the seam, some distance. So GG dash is, what is the GG dash? So GG dash is nothing but GM tan theta. GM tan theta. Because if you take it, GG dash by GM is equal to tan theta. So from here, GM value is another way you could be able to find it, the metacentric height for the loose weight, Px into W tan theta. That is another expression for the metacentric height. But we are going to discuss now what is the importance of the metacentric height. Again and again, I am telling this metacentric height, you should keep as much as high possible, then the stability will be maintained. For the sake of the stability, the metacentric height should be positive. That means the aim is above aim is above G. That is a positive. Next, we'll see some problematic will come. After that, we'll do some problems regarding this views also. But another thing is the GM. If it is less than 0, that means M is below G, so instability. So here we conclude that metacentric height GM should be as much as high possible for the sake of the stability. Next lecture, we now finish here. Next portion, we will see how the metacentric height we are compromising with our comfort level. And we'll go for some problem also regarding this topic. So we'll come back just now. So we have seen this thing, the metacentric height expression in two terms. That is all we are discussing. So just to again rewrite this equation, what are the equation we are getting regarding the metacentric height for here. So it will be, gives you the clear ideas. So the metacentric height GM, we are getting if the floating body, that is most important equation, Iyy by volume minus Pg. That is one expression we are getting. The most important equation. Most of the expression comes by here. Another, the metacentric height we are getting from the loose weight. This loose weight, if they're loose weight, it displaced by x. So, and W is the total ship which is floating into tan. Here's another expression. It is coming from experimental view. This is coming from experimental view. Moreover, we have to ensure there should be sufficient GM greater than 0 for the sake of stability. When instability comes, instability will come when GM value is less than 0. That is the condition for instability. And this is the condition for stability. Okay. Now we'll see one thing. Rolling, pitching, everything we'll see. But here you see the rolling. Rolling is just we are considering that it's a rolling here. Whatever. So about if the ship is looks like in this way. If you see the ship is looks like in this way. There's a ship. So about this axis, if it is moving, the axis symmetry about this axis, and if it is roll, that is the rolling. Rolling. Whatever we are considering now, that is the rolling, and this is the pitching. So in the rolling or pitching, if the width, that is the width W, and length is L. The width of this, it is the W, and length is the L. So it looks like a rectangle. So which axis? The rolling axis is this, the rolling axis. This axis is the rolling axis. It is a Y, you name it Y. So Y axis is the rolling axis, and X axis is the pitching axis. X axis is the pitching axis. So what is IYY? So IYY here is the, because Y axis is dividing L like a cube by and the pitching axis IXX. This one. Better to write it IYY, it is the I rolling. Better to write I rolling. Is the I pitching. Rather than to write it XXYY. We can change XY. We can take this as a X, this as a Y. No changing. So better to write it I along rolling. So inertia, second moment of area, I rolling, and I. Which one is more? Here, L is much more greater than, length would be much more greater than the width. So I pitching will be greater than the I rolling. I pitching will be greater than the I rolling. So which is more sensitive case? We'll see. Just one concept I am giving. I pitching is less than I rolling. Now GM value is I by S. So for the case of the rolling, GM of rolling, metacentric height during rolling, I rolling, and GM pitching, I pitching, So as it is less, so this is more critical. This is more critical because there is this GM metacentric height for the rolling. There is the most chance to getting sink or for instability, because instability of the seat will cause for the sink. You go inside. So GM rolling, metacentric height for rolling is most critical than the metacentric height for the pitching. So that's why you have to choose this concept. Similarly, here the rectangular pipe is given. So which axis you have to choose? What is the y-axis? Which axis you have to choose? That's also which one. About the axis, the moment of inertia is the minimum. This is you have to choose. So here, if you so which axis you have to, in the plan view, which axis is the y-axis? Whether this axis or this axis. Where the moment of inertia, I value is less. I value is the less is the critical case. Is critical. Where the second moment of floating area about the rotational axis is lesser, you have to consider this thing. That is most critical for the GM or metacentric height. So this way you have to choose it. One more thing, the natural frequency concept we'll see now. The metacenter. So your previously here was the G. Okay. So what is happening here? You see that is the central line. Central line. So give one rotation in this direction. It is over the central line. Okay. So you give one rotation. Now we'll see the vibration concept here. How vibration is coming into the picture. So as we give one theta in this direction, so on the opposite direction, inertia torque will be act over. What is that? Inertia torque. If you remember, that is this. Similar like inertia force, mass into acceleration. So inertia torque is the moment of inertia into angular acceleration. Will be opposite direction and back. Next thing, here weight is at G, the weight is acting W. Because of the W force on node, it is acting W into GM in this direction, because it will create rotation in this direction, anti-clockwise. So anti-clockwise to rotation from the D'Alembert's rule, that is equal to 0. If you remember the vibration portion, it is like that. And theta is considered the small. So sine theta equal to theta. So I theta double dot plus W into GM into theta is equal to 0. So theta double dot W into GM by I This equation is similar to this equation. Omega n square, we can say. So omega n is the natural frequency. We can compare these two equations and we could be able to write it omega n is equal to W into Gm okay. W into Gm by I. So it's just like a spring mass system. If you think about the spring mass system, one mass is there. Here one spring. So if you give one force displacement in this side, opposite direction inertia force is acting m double dot, and here because of the spring another force is acting here, stiffness kx. So m x double dot plus kx is equal to 0. So m double dot is equal to k by m 0. Omega n is equal to lower of k by m. Same way we are getting this thing. Natural frequency of the floating body is a harmonic in nature, this frequency. But one more thing you see, for the sake of stability, we want to keep Gm is higher side. We try to raise the Gm value. But if you increase the Gm, metacentric height, your omega n also will be increased. What does it mean? Your natural frequency will increase. So that will create the uncomfort for the passenger. So for the sake of the comfort, you have to compromise slightly with your stability, because it will create too much uncomfort for the passenger. Because as you increase metacentric height, you can see from this expression, your omega n is also rising. Natural frequency. So that is why, for the sake of the comfort, so Gm is kept slightly lower, but it should be always greater than 0. This is the consideration and concept in here.